So we've been talking about systems of equations. So we've looked at several different methods. We looked at graphing systems, which is quick, simple method, but not very precise. Then we looked at algebraic solutions. We looked at substitution, where you solved one of them for a variable and then plugged it into the other. And then we looked at the elimination or addition method, where you had to adjust the equation so that one of the variables canceled out when you added down the columns of that system. So let's take a look at a system and review how to solve. Looking at this system of equations, what would be the easiest method to use to solve this system? Why would you say elimination or addition? Now we've got negative 3y and positive 3y. Our columns already lined up. We have x's, y's, equals, and then a constant over here. And the negative 3y and positive 3y are going to cancel out, become 0. So we'll go ahead and add our columns. 2x and 5x make 7x. Negative 3y and positive 3y cancel out. Equals, and then 13 and 1 make 14. So we have 7x equals 14. We're going to divide by 7. X equals 2. Now what do we do with that x equals 2? We got to find y by plugging that in for x. We can put it here or here. Since I prefer to avoid negatives, I'll use the bottom equation since everything's positive. So 5x becomes 5 times 2 plus 3i equals 1. 5 times 2 is 10. We will subtract 10. 3y equals negative 9, and we will divide by 3. Y equals negative 3. 2, negative 3 is our solution. Looks familiar, right? Well, today we're going that next step. We're adding a third variable, z. Now, when we add a third variable, we have to add a third equation. We need to have an equation for each variable so that we can solve it. Let's see. So let's see here. There's our system. Now we could use substitution. We could use elimination or addition. We could graph, but when you graph a 3-variable system of equation, it is really tough. Let me give you a little example here quick, just to give you an idea of how 3-variable graphing goes. You have x and you have y. Picture that as laying flat on the table and you're like looking at it from off on the corner. And then z goes straight up out of the table and straight down into the table. So just to plot the point, like 3, 2, 5. So x is 3, so on the x we go 1, 2, 3. What's that? Kind of, yeah. Y is 2, so on the y we go 1, 2. Z is positive 5. 1, 2, 3, 4, 5. Well, what we got to do is we got to trace from z over. From x, we got to trace from z in each direction along parallel to each axis, like that and that. This one here is parallel to this axis. This one's parallel to that axis. We gotta do the same for x. I'm gonna use a different color. I'll do x. Trace it parallel to that axis, parallel to the z-axis, like that. And then the same for y. Trace it parallel to this axis, parallel to the z-axis. And what we get here is the makings of a cube. We'll finish it off. Trace this up, this over, and that's it. That is the point. X is 3, y is 2, z is 5. But if I just put a point there, there's no, without having that box there to trace back, if I just put a point there, there's absolutely no way to tell what point that is. So we can graph these equations all we want to. We're never going to be able to see where they all cross and come together. It's just not going to work. I mean, just graphing a single point here requires a lot of auxiliary lines to know what it is. And you saw how long it took me to plot a single point. I don't expect you guys to be able to plot points on a three-dimensional graph. But be aware that that is what that represents. And you can kind of see it when I put the little dotted lines in there. It's just not fun. So, what are we going to do? Well, as I said, we have two options. We have substitution. We have the elimination or addition method. Let's try to solve this one using substitution. If I were using substitution, first thing you have to do is pick an equation that you're going to solve for one of the variables. I am going to solve equation C for x. Can anybody see why I'm going to solve equation C for x? Well, there's no negatives, but also x is just 1x, right? I don't have to divide by anything. Could have solved equation A for z as well, would have worked just as well. But I saw the x first. So if I solve that for x, x plus 2y plus 3z is 16. I have to subtract 2y from each side. So I still got x plus 3z equals 16 minus 2y. And I need to subtract 3z from both sides. X equals 16 minus 2y minus 3z. That's equation C solved for x. Now, so I've used equation C. What I need to do now is I need to use each of the other equations combined with that. So equation A is going to become not 2x, but 2 times 16 minus 2y minus 3z minus 2y plus z equals 13. We now have a little bit of work to do here. So let's do it. 2 times 16, 42. 2 times negative 2y, negative 4y. 2 times negative 3z, negative 6z, minus 2y plus z equals 13. Well, we're combining negative 4y with negative 2y makes negative 6y. Negative 6z and positive z make negative 5z. We've still got that 32 up front equals 13. And now we shall subtract the 32. The reason we're subtracting the 32 is just to get all the constants on one side, all the variables on the other. So I have a negative 6y minus 5z equals a negative 19. If I wanted to, I could multiply everything by a negative 1 and make it 6y plus 5z equals positive 19. But we'll see if we really need to do that in a little bit. Next, I'm going to come back to equation B. And instead of 3x, it's going to be 3 times 16 minus 2y minus 3z minus y plus 2z equals 20. Now again, we've got some work to do here. 3 times 16 is 48. 3 times the negative 2y, negative 6y. 3 times negative 3z, negative 9z. Then you got a negative y, positive 2z, equals 20. So the 48 don't change. Negative 6y and negative y. Negative 7y. Negative 9z and 2z. Negative 7z. And we shall now subtract 48 to get all the numbers on one side. So negative 7y minus 7z equals a negative 28. Now in that equation, I see something very, very significant, and I'm going to take advantage of it. Bless you. This is negative 7, negative 28. What can all of those be divided by? All be divided by a negative 7. So it gives me a positive 1y. And a positive 1z equals a positive 4. That's a much simpler equation to work with. Now if I come back up here, I've got the negative 6y minus 5z equals a negative 19. I got a straight line for no apparent reason. And I've also got y plus z equals 4. Now looking at this, I can still use elimination. I just have to do a little more work. This bottom equation, I can either get rid of the y or the z. It doesn't matter. I'm going to get rid of the y. I'm going to multiply by 6. So that's going to be 6y plus 6z equals 24. Everybody see where that came from? 6 times y is 6y, 6 times z is 6z, 6 times 4 is 24. Then I still have negative 6y and minus 5z was negative 19. Negative 6y and 6y cancel out. 6z and negative 5z is just 1z or z. 25 and negative 19 is 5. Z equals 5. Now that we know that, we can come back here. Y plus 5 equals 4. Replacing the z with a 5. Minus 5. 5 equals negative 1. Then going back to one of our original equations, it doesn't matter which. I'm going to do the bottom one. X plus 2y plus 3z equals 16. And I'm going to replace y with negative 1, so this is 2 times negative 1, and z with 5, so it's 3 times 5. So 2 times negative 1 is a negative 2, 3 times 5 is 15. Negative 2 and 15 make 13. We shall solve this by subtracting 13. X equals 3. So x is 3, y is negative 1, and z is 5. What you think?
Yeah, that's a lot for 13.
Once we decided that we were going to solve equation C here for x, come on. Once we decided we were going to solve this one for x, that meant once we solved it for x, we're going to have to put that in for x in the other two equations. Yep. Yep. Now I'm going to show you a little bit different method now. When it comes to these three variable systems of equations, there is no denying it is a lot of work. No way to get around it. It's going to take some room on your paper, period. But depending on your preferences, some ways are easier than others. I don't like using substitution, yes.
How much easier would that be with elimination?
That's what we're going to do now. I don't like substitution. Some systems, it's the easiest way to do it. If I see that, I'll do it. But if it's ambiguous, if there's no easy way to do it, I usually default to the elimination method. So let's label this equations A, B, and C again. Just like before, we have to go variable by variable and think least common denominator. Now, if we look at this, the x's here, 2, 3, and 1, we'd have to turn those into 6's, wouldn't we? That's not bad, not horrible. If we look at the y's, negative 2, 1, and negative 1, and positive 2, we'd be changing those into 2's is all we'd have to do. That one's actually pretty easy. In the z's, you got 1, 2, and 3. Well, just like x, you'd have to change those into 6's. That's not bad either. But to me, it appears that y is going to be the easiest candidate. Now what I have to do is I have to, just like we picked an equation to solve for x in the substitution method, now that we've decided we're going to get rid of y, we have to pick one equation that we're going to use to get rid of y in the others. And I'm going to pick equation C again. I could have picked equation B. Equation B would have worked well as well, because that's a 1 and the others are both 2's. The reason I'm picking equation C is because that one's positive y and the other two have negative y's. So now, if I do equation A and equation C, 2x minus 2y plus z equals 13. X plus 2y plus 3z equals 16. What do you see is going to happen to the y's? They automatically disappear without having to do any adjustment. So 2x and x make 3x. Negative 2y and positive 2y disappear. Z and 3z make 4z. 13 and 16 make 29. So 3x plus 4z is 29. So next, we're going to use equation C again, but we're going to use it with equation B, but not just equation B. We're going to use equation C. X plus 2y plus 3z equals 16. We're going to do 2 times equation B. Why 2 times equation B? It's a negative 1, and we want to make it into a negative 2. So 2 times 3x is 6x. 2 times negative 1y is negative 2y. 2 times 2z is positive 4z equals 2 times 20 is 40. It is very, very important that you eliminate the same variable both times. We eliminated y here. We have to eliminate y here. Also notice, one equation gets used twice, but the other 2 equations must get used once in each of them. Okay? So now, x and 6x makes 7x. 2y and negative 2y cancel out. 3z and 4z make 7z. And 16 and 40 make 56. All of those can be divided by 7, which will give us 1x, or just x, plus z equals 8. And then, of course, we still have 3x plus 4z equals 29. You will notice that in both methods here, the first part is to turn this from 3 equations with 3 variables into a system of 2 equations with 2 variables. I did the exact same thing up here with the substitution. Where was I? Right here. I got 2 equations and 2 variables. And had to do the elimination with those. So now I have to figure out some way to get rid of one of these variables. I could solve one of them for x and put it in, or what I'm going to do here is I'm going to multiply this bottom one by a negative 3. So it's a negative 3x plus a negative 3z equals negative 24. So the top equation still stays 3x plus 4z equals 29. And when we add 3x, negative 3x and 3x go away. Negative 3z and 4z make positive 1z. Negative 24 and 29 makes 5. Z equals 5. Yes?
Is that just some number that you come up with when you decide what time the equation that x plus z equals?
Yeah, when I do the negative 3.
Want to run with it? Or
Yeah, what it is, I look here and I see, hey, this is a positive 3x. If this were a negative 3x, it would cancel out. So I make it a negative 3x. I could have also multiplied by negative 4, so it would be positive 4z and negative 4z. That would have worked as well. So once I know that z is 5, we've got to find x and y. So I'm going to go back to this equation here. X plus z becomes x plus 5 equals 8. Subtracting 5 gives us x equals 3. And then go back to one of the originals. X plus 2y plus 3z equals 16. X is 3. We're looking for y. Z is 5. So we have 3 times 5 is 15. So combine the 3 and the 15 to make 18. And then we shall subtract 18. 2y equals negative 2. And finally, we will divide by 2. Y equals negative 1. So x is 3 when y is negative 1 and z is 5. The exact same answer we got with substitution, which is good because the answer shouldn't have changed. I think elimination is a little simpler. Substitution is a lot more work at the beginning, but once you have one of the variables, it's quicker to go back and get the others. Where elimination, it's quicker at the beginning, but once you have one of the variables, it's a little more work to go back to get the others. But I always preferred elimination. You guys can use whatever method you want. You are going to get a worksheet with 8 of these systems of 3 variable equations on them. Feel free to solve all 8 of them if you want.
Feel free.
Feel free.
If you want.
If you want.
Awesome.
You might want